So yesterday we got some exercise about methanol manufacturing, okay, in which the problem statement was about manufacturing or design the plant. Okay, so how will we do that? So it's like a PO, a post order that we get from our customers. So we have a product specification that design capacity is 1000 tons per day, okay, and the feedstock is carbon monoxide and hydrogen, okay. Reaction is given and the conversion that is 30%, okay. So space velocity and of catalyst 5000 meter cube per hour was given, and properties of steam and CO, methane, CH3OH and CO and H2O was given, the molecular weight and all, everything was mentioned in the PO. So some things were missing that so the first deliverables was flow sheet, simple flow sheet, how the plant will look like, what will be the necessary things that we will discuss in the flow diagram. Then we have to consider all the instrumentations related to the flow sheet, everything including valves, safety measures. Then we will see what will be the controllers we will be using in the flow sheet. Then a small process description, how the process will look like, how methanol will be produced from CO and H2, what will be the reaction parameters and everything. There will be a material balance for this, okay. We will discuss about how much amount of CO and H2 will be required for creating our product. Power consumption, as we have more compressors and everything in the inline construction, so we will be discussing power consumption. The reaction is exothermic, so we will be evaluating the cooling duty for the heat exchangers and everything. And lastly, we will be estimating the capex estimation for the plant and operating expenditure and product price, okay. So this is the first PFD, that was the first point to be evaluated. The carbon monoxide and hydrogen was passed from by a compressor, okay, and it is compressed to 50 bar as mentioned in the problem statement. Then it sent to a reactor where reaction takes place and methanol products formation, and from reactor it is the exothermic reaction, so we have given the heat exchanger, okay. It is withdrawal from the reaction, and from heat exchanger it goes to separator. And what happens is separator, that unreacted unreacted carbon monoxide and hydrogen again goes back to the inline stream. It is recycled and compressed back again to save the cost and everything, okay. And the separated methanol is collected in the collector, it's methanol collector. And talking about the detailed PNID, then CO and H2 are passed from the MFCs, that is the mass flow controller, okay. And then it is the FM is like flow meter, what is the flow that is given or indicating the amount of liters per minute is the CO and H2 flow. Then it is compressed to 50 bar, and there is a pressure transmitter which will be indicating the pressure to the PID controller system or SCADA system that will manage the pressure, okay. And then this compressed stream are sent to the reactor. The reactor is jacketed reactor to cool down the reaction, since it is exothermic reaction. So we have a cooling water in and cooling water out for the reactor system. We have a pressure relief for PRV, because it is exothermic, the pressure will be building in the reactor, okay. So for safety purpose, if anything fails, then PRV will be there to handle the cause, okay. Then PT is mentioned, that PT is for pressure transmitter, okay. this pressure transmitter will transmit any digital signal to system, that PID system. Then temperature sensor is required, since we have to regulate the temperature of the exothermic reaction. Okay, and the for manual oversight, the pressure gauge is given. Okay, then after cooling, after the reaction occurs, the outlet temperature of the reaction is measured. Then that's why, for that reason, the temperature sensor is given for outlet stream of the reactor feed. Okay, and after measuring the temperature, the heat exchanger will be given, means amount of flow of water will be mentioned. Okay, so that it will regulate the temperature lowest as required. And after cool down, again the temperature sensor is given to detect any changes in the temperature. Okay, then for separator, we have gas and liquid both phases. So pressure gauge is given again, and the gas is the unreacted methane, carbon monoxide and hydrogen is again compressed back and sent to the inline stage. Okay, and there is also a pressure transmitter here on the recycle stream. And after separator, the pump sent the methanol into the tank, and here a level indicator is given. Level indicator and level controller both are given.
So before we move to next page,
Yes.
so comments from other groups. Anything you like, positives, anything they missed, what your group included? No? Okay, please.
Thank you. Then the second point was to material balance, do material balance. Okay, so we have a reaction like CO plus 2H2 gives CH3OH, and the heat is evolved. So 128 megajoules per kilomole of heat is evolved. Okay, so design capacity is 1000 tons per day. The 1000 tons per day is converted into kg per day, 10 to the power 6 kg per day. Okay, for simplification of the calculations. So moles of CH3, 10 to the power 6 by 32, because so the molecular weight of CH3 is 32. Okay, so we are going to produce around 31,000 to 50 kilomoles per day of methanol. Okay, so CO, carbon monoxide needed is the same, since 1 mole of CH3 is produced, 1 mole of CO is consumed. So same amount of carbon monoxide, and for H2, twice moles of H2 is given to the means reacting. So twice of CO or CH3OH kilomoles. So 62,500 kilomole per day of H2 is needed. So we have given that the 30% of conversion is there. So for 30% conversion, the total amount of kilomoles reacting divided by 0.3%. Okay, so 0.3%, it goes to 1,04,167 kilomoles per day of CO is required. Okay, and for H2, it's 20833 kilomoles per day of H2. Now that we have the CO and H2 are reacting around 30%. Now we have unreacted CO and H2. Okay, so 72,000 divided by 7.7 for the same amount. Then 7,29,000 of kilomole of per day of CO, and 1,45,000 of kilomole of H2 kilomole per day. Okay, then we come to power consumption. Okay, power consumption, the compression duty was given. Okay, so we have the tons per day of production. kg per day of production, 1000 tons per day. Okay, so the pressure that we have to build was 50 bar. Okay, and the power consumption duty was given 5000 kilojoule per ton per bar. Okay, so it is for 5000 was for 1 kilojoule per bar, per bar. Okay, so we have to multiply it by 50 bar. Okay, and the amount of production we are doing, so 10 to the power 6. So the power come around 2.5 into 10 to the power 11 kilojoules per day, and for in kilowatt it was 2430. Okay, and same for pumping power. We have given that pumping duty was 100 kilojoules per ton. Okay, per bar, and same for same calculations as 50 bar has to be up to 50 bar it has to be pumped, and the production, so it gives around 50 into 10 to power 8 kilojoules per day of power means required, and the cooling duty for the heat exchangers and all. So the heat evolved, we have production of methanol around 31250 kilomoles per day of methanol. So same has to be taken, and the heat revolved was 128 megajoules per day. So it is just it has been converted to kilojoules per day only. Okay, so 128,000 kilojoules per day, and it comes around 46,296 kilowatt of heat cooling duty. Sorry. Capex estimation will be done by.
Sorry?
Capex estimation will be done.
Okay.
So for capex estimation, like while considering capital expenditure, we consider all the factors like how much of the metal we are needing for the reactor, so cost of metal, other equipments. So overall we have considered here capex estimation to be 50 million for our plant. So discussing the product price, let us assume the profit to be of 10%, and a depreciation of 15 years is considered here. So while deciding any product price, we consider three factors like operating cost plus its capital cost plus profit. So the H2 price was given, it was 1.5 euro per kg, which is 1500 euros per ton. The LHV for H2 was for CO was given 10 megajoules per kg. Rather we later on we got the value of for H2 it was 120 megajoules per kg. So so we calculated H2 price upon LHV for H2, like for how much euros will be required for 1 megajoule of H2 to be to generate that much amount of energy, and the same ratio was compared to the CO price upon LHV of CO, which gave us the price of CO to be 125 euros per ton. So the operating cost was found to be 1500, which was the price of H2, plus 125 price of CO, and 5% more price, more or less, to be it was considered for extra materials, and the capex was 9.05 euros per ton. It was calculated by 50 million divided by the depreciation of 15 years, and it was converted to euros per megajoules. So the overall and a 10% profit was considered here. 10% of the total cost was evaluated to be considered as the profit. So the final product price was 1885.925 euros per ton, which was much more. Later on we got that it was 360 or something euros per ton. So this was a complete description.
Okay. Good. Thank you very much.
Thank you, sir.
So comments once again from other groups. If you can turn the page on the PFT. Yeah. So what was really good, they thought about all the equipments. They started with the reactor, and across the reactor they thought about separation. So you remember this onion model, you start with the reaction system, then separation. Probably they thought about utility, U, but maybe one small comment. You probably missed the heat integration. The operating temperature of the reactor was 300 degrees centigrade, and we said you always extract heat at highest temperature possible, and you could have done it with steam generation, right? So it's not wrong, it's not right, but that's how you can probably your 1895 euro ton would have been 1500 euro tons, right? So that's how you could bring down, you could have brought down your product price, right? So very good. You thought about safety, so PSV is there. You thought about already how you want to operate the plant, what parameters you want to keep eye on. So PG, not only PT in the control room or SCADA, but you also put a PG. If operator is walking around in the plant, he is not in front of control room. Even in field, he is aware. So there is a local pressure gauge. So very good thinking. And you also had a tank. So probably this is about this buffer volume for day or two required. So you produce your methanol and then it goes to the tank. So all in all, very good. I'm very pleased to see that you gathered something from last 2-3 days and try to apply all those things here. So thank you.
Thank you, sir.
Then there is another piece, but I do not have a name. It's very well written. I think those were yes. Piyush, Yogini,
Yes.